In this math talk, we're going to introduce some formulas for what we call analytic geometry. Now, analytic geometry is a little bit different from the grade 9 Euclidean geometry that we studied for plane figures like triangles and trapezoids and parallelograms, where we used Euclid's postulates basically to prove things. For example, proving that, opposite sides of a parallelogram are equal. We are going to change the way we do this by taking our geometry and putting it on the Cartesian plane. So we begin by taking the xy plane and we place 2 points, P and Q, on that xy plane. The coordinates of those points are x1, y1, and x2, y2, and we connect a line segment between them. Now, just reading down to the axes, we can see that point P has this x-coordinate x1, and point Q has this x-coordinate x2. And we recognize that the distance between these 2 points, and when I say the distance between these 2 points, or these two x values, I'm referring to the horizontal distance, can be expressed as x2 subtract x1. We now do the same thing for the y-coordinate, recognizing that point P has a y-coordinate of y1 and point Q has a y-coordinate of y2, and the vertical distance between those 2 points is y2 subtract y1. And now we become very interested in this right triangle that I've marked in yellow, connecting the 2 points P and Q. What we need to recognize is really we have 3 sides to this triangle. We have the side PQ, which represents the hypotenuse. We have the vertical side, which is y2 subtract y1, and we have the horizontal side, which is x2 subtract x1. Well, very quickly we get our old formula that we developed. When I say old, we developed it back in grade 8 or grade 9, that related the slope or the gradient, the steepness of the line segment PQ, to the coordinates. And we base it on the concept that slope is rise over run, comparing how much you travel up and down versus how much you travel horizontally as you move from point P to point Q. And so we say slope PQ is rise divided by run. Well, substituting for the sides that we have marked in blue and red, the rise is y2 minus y1 and the run is x2 subtract x1. And so we have the slope of PQ, which we call MPQ, is y2 minus y1 over x2 minus x1. Pretty straightforward stuff that we've worked on before. Now, the second formula I'd like to develop is the distance or the length of the line segment connecting P to Q, the distance from P to Q, effectively. Well, when I look at that diagram, I recognize that it is a right triangle, and I understand that in right triangles, we have something called the Pythagorean theorem. And the Pythagorean theorem states that the square of the hypotenuse is equal to the sum of the squares of the other 2 sides. So if I were to express that for the diagram that we have here, we see that the length of PQ squared would be equal to the run squared plus the rise squared. Well, we can then substitute for the run and the rise and take a square root, and we understand that the length of PQ is the square root of x2 minus x1 all squared plus y2 minus y1 all squared. And that's our second formula. The third one that we like to come up with, which is very useful when we talk about certain characteristics of triangles, is the midpoint formula. And let me just add a bit of a construction here. I've placed a point midway between P and Q. And for now, I'll mark that point M. Now, if you were to take a look at the x-coordinate and the y-coordinate for that point, you might be able to reason out that the x-coordinate lies halfway between x1 and x2, if point M lies halfway between P and Q. I think that makes intuitive sense to most people. So the question is, how do we find the halfway point between x1 and x2? Well, that's really just simply the average of x1 and x2. And what I'm saying here is that we take x1 plus x2 and divide by 2, and that would give us the x-coordinate of M. Similarly, we would do the same thing for the y-coordinate, so we'd have y2 plus y1 all over 2. And so we have a formula for the midpoint, which is x2 plus x1, and we could have written that in either order, x1 plus x2 or x2 plus x1 over 2, and y2 plus y1 over 2. And those are the three key formulas that we're going to use to answer a lot of our problems in analytic geometry. Let me go a little bit further and develop equations of lines. So now I will draw the line that passes through points P and Q, and I'm going to pick an arbitrary point A, which I will call XY. That could be any point. That red point could be any point on this line passing through PQ. What I would like to do is find the equation of that line passing through P and Q. And there are a variety of ways to do it, but I'm going to do it this way just because it's a little bit different. Not all teachers will teach it this way. I just want to show it to you this way. I think you would agree that no matter where I place point A, the following would have to be true. The slope of the line segment that joins A to P, so MPA, has to be the same slope as A to Q, the line segment joining A and Q, if they all 3 points lie on a straight line, or they are what we call collinear. Well, that being said, if I substitute for the slope of PA and the slope of AQ, I get the following expression, that x2 minus x over y2 minus y is equal to x minus x1 over y minus y1. Now, the next step involves a little bit of algebra, but it's not too bad. I'm going to cross multiply these two ratios that I have, and that will look something like this. I'll multiply x2 minus x1 times y minus y1 and say that that has to be equal to x subtract x1 times y2 subtract y. Now, if I expand by just using the distributive property, or what we often call with binomials FOIL, I get the expression on the left and the expression on the right. And I would encourage you possibly to pause the video and verify that you get exactly those two expressions. From that point, I simplify by recognizing I have a negative xy on both sides of the equation, so that will disappear, and that's kind of handy actually. And then I gather on one side of the equation all of the red y's, that's the variable point y, and on the other side of the equation, all of my red x's, in other words, the x coordinate of point A, and all of the leftover stuff, the x2, y1, the minus x1, y2. And now I'm going to do a little bit of common factoring. And so we get, on the left-hand side, y times x2 minus x1 equals, on the right-hand side, y2 minus y1, x plus x2 y1 minus x1 y2. Now, what's kind of interesting is that x2 minus x1 looks very familiar, and the y2 minus y1 looks very familiar. Next, what I'm going to do is divide both sides by the x2 subtract x1. On the left, we just have y, and on the right, we have the expression that you see. But what you notice in front of x, the red variable x, what you notice is you have y2 subtract y1 over x2 subtract x1. Well, that in fact was our slope. So that can be replaced just with m. And then the second part of that expression just involves the x1 and x2, the y1 and the y2. That is just a calculation that you need to perform to get a single value. That will come out to a value that we will arbitrarily call b. Now, that form is very familiar to us. We remember last year learning about y equals mx plus b, or the year before you learned about y equals mx plus b, recalling that the m represented the slope of the line through P and Q, the slope of that line, and b ended up being the y-intercept. And so all of that algebra really reduces to y equals mx plus b. So the good news is we now have a fourth formula that we're going to use for doing our problems. But I want to show you one other thing that we could have done with that last development. We could have taken the expression that we had with the x and the y factored out. I've reversed the left and right hand side. And I could have gathered everything to one side of the equation. So I would have had an expression looking like this. Now, once again, you might want to perform this on your own to verify that the first line leads to the second line. Now, I told you that y2 minus y1 and x2 minus x1 certainly look familiar, and they do. They really represent the rise and the run. So really what I have is rise x minus run y plus, and that x2 y1 minus x1 y2 is just going to be some constant. It's just a calculation that I'm doing with the x and y coordinates. And so I get this simple sort of expression where I have the rise times x minus the run times y plus c has to be 0. This is another form of the equation of this line. Now, one other manipulation that I will do will be this. I will turn it into rise x plus negative run y plus c equals 0. I'm going to call the rise arbitrarily a, the negative run arbitrarily b, and leave the c as it is. And I get ax plus by plus c equals 0. And that, in fact, is what we call the standard form for the equation of a line. So buried in that standard form is rise and run. The a is the rise and the b is the negative of the run. And that can be kind of handy when you're looking at the standard form for the equation of a line. You can pick that right out. And so we have our standard form, we have our y equals mx plus b form, and we have something that's called point slope form. And I'll get to that more when we do some questions. And that's coming up next, but I'm probably running over time at this point, and so I'll put my examples in the next video. Thanks for watching. See you soon.